The 9 warrants for the traffic signals, and we tried to apply them for an example. Okay, and we couldn't apply all of them because of the data which was given, and we moved on to this thing where I explained some of the terminologies related to the signal. Okay, so the smallest time period in the signal is an interval. Here you see one light. When you combine different lights, becomes a phase. When you combine different phases, becomes a cycle. And then for each cycle, you have a lane group. Okay, the lanes which are going on in the same phase. And for every lane, you have a saturation flow rate, the ideal flow rate, without any delay, without any signal. And then you have the capacity, which includes the signal stopping and everything. Okay, so saturation flow rate is ideal, and capacity is the real one. And then you can calculate volume to capacity ratio as well as volume to saturation flow rate ratio. I explained these terms as well. Okay, lost time, effective green. Okay, for every phase you have a critical lane group which will dictate the timing. Okay, sometimes you have overlapping phases. The movements can be permissive, protected, or they could be combination. If you are allowing left turning first and then the straight, it's called leading. If it is the other way around, it's called lagging. Now, for every intersection, we can perform a quick analysis for the capacity of the entire intersection, and we can know the state according to the traffic flow. Okay, so what is the current traffic flow and what is the capacity? There's a quick method to compare between them, and that is called as critical movement analysis. Okay, so in critical movement analysis, we can quickly calculate the capacity of the intersection, and we can quickly compare it with the volume to see the state of the intersection. It's a less accurate but fast method of analyzing the intersections. Okay, so it is less accurate but very fast. Okay, so we use it when the design is not yet ready. Okay, so once the design is ready, then you can perform more detailed calculations on it. But initially you can use this quick method to know if what would be the condition of your intersection. Okay, so the saturation flow rate which is normally taken for this analysis is 3600 per hour. Okay, and to adjust for the lost time, okay, because we know at the intersection vehicles will come and they have to stop and so on. So to adjust for the lost time, you can reduce it by 20%. So you can actually take 20% of 3600. So where can we use this critical movement analysis, the quick method? You can use it at the planning stage, not at design stage. Okay, because it's very quick and does not require a lot of data. You can, if you are comparing between different options. So I cannot do a detailed design for all the options and then compare. So I will, for these options, I will do this quick method to see which option is better, and then I go for the design of that option only. Okay, you can use it for initial timings, initial plans of the signal. Okay, later on that can be improved. You are doing calculation using a software, but it's a new software. You are not completely sure about the results. So to do the entire calculation which the software is doing, it will take double the time which the software has already taken. So you will eventually waste a lot of time. So what we can do is do the calculation in the software, then do this quick method manually, and then you can see if the results are close enough or not. Obviously they will not be same. Software and manual results are never exactly same, but this method gives you an idea that if the software is giving reasonable answers or not. The last one I already mentioned. Okay, these are the 6 steps which we follow for critical movement analysis, CMA. First of all, you have to identify the movements which are allowed from the intersection, and for each movement you have to find out volume per lane, how much volume in each lane. Okay, and they should be in, then you convert it to flow rates. The volumes are converted to flow rates. This is what they mean by adjusted to peak 15 minutes. Okay, this means convert the volumes to flow rates. Then you assign the movement to each phase sequence. Then you determine the critical volume pair. What is the critical volume pair? The conflicting movements which will happen one after the other. The conflicting movements which happen one after the other. So if you have this one and this one, okay, so these are two movements and they cannot happen together. Okay, so that it will become a pair. Okay, and you will select the pair which gives you the highest movement crossing that point. Okay, then you sum the critical volumes for each phase, and then you identify the maximum critical volume. For maximum critical volume, which is the capacity, basically they have given us some guidelines. Okay, you can take it 1400, 1530, okay, in different situations, but it's normally around 1400, 1600, something like this. And then you can calculate volume capacity ratio and find out the status of the intersection. How do you find out the status of the intersection? Based on volume capacity, these are the ranges we follow. So more than 85%, more than 1% is obviously oversaturated. Volume is more than capacity. 0.95 and 1 is very close to capacity, almost capacity. 0.85 and 0.95 is near to capacity, and less than 0.85 is considered under capacity. So for less than 0.85 is something, is a situation where we will fail, we will feel safe. Okay, sorry for that. We will feel safe. Okay, if it is less than 0.85. Okay, let us apply this to this intersection. Okay, we have two examples for that. So you can see different movements are given. Okay, for east and west and north and south. You can see that the movement which is on this side, on the west side, it is termed as eastbound. It is going towards east, it is facing east, so we call it eastbound. Similarly, this one is westbound because it is facing west, and so on and so forth. Okay, now the volumes are already given. Okay, they are already given, and we need to find out the critical volume pairs. Okay, so the first step is already done. Movements are identified. Okay, and the volumes are already given. Now we have moved to the third phase. We phasing sequence will come with that. Okay, so let me just quickly check something. Okay, okay, so one pair of movement can be between east and west, the other pair can be between north and south. Okay, so between east and west we can have, so you can see the left turning for west can conflict with the straight and through of the right. West turning of the left can conflict with the straight and through of the right. Okay, so this will be one pair. The other pair will be the opposite. Left turning of the eastbound and straight and right of the westbound. Okay, the straight is also called as through, so keep this in mind. So we have two pairs, one with each left turning, and the same for north and south as well. Okay, so we go there. So the first pair is eastbound through and right plus westbound left. So eastbound through 585 plus yeah, through 585, and then we have uh, the 275 for the west. Okay, and then again I need to check something. Yeah, okay, so this one will be taken as half. Okay, and this one will be taken as full. Whereas westbound one. Okay, why this one is taken as half? Because you are distributing the time. Okay, so half of the time will be available for this one. Okay, and the remaining will be for this one. Okay, so this is the distribution of the time basically. Okay, whatever timing you will give in the signal, half will be consumed by this and the remaining by this. So that's why we are dividing by or multiplying by 0.5. So this indicates the half of the time available for this one. Okay, so and the other pair will be westbound and eastbound. So eastbound left is 130 and westbound 496. Okay, similarly we can do the same thing for north and south as well. I want southbound through and straight. They will intersect. That's why we are dividing the time, right? We are dividing the time. That's why 0.5. So when this will happen, this will not happen. Okay, so this is why 0.5 factor is there. Okay, so northbound left. Where's northbound left? 95. So northbound. And then we have southbound left. Okay, so what do we have? Yes, can you give me these values? So they are in the same order, huh? Okay, so now either this can happen or this can happen. Like this will happen in one phase, or this will be one combination of phase, and this will be the other combination of phase. Okay, so either you can allow, or in one phase you will allow westbound through. okay, and the conflicting phase, the other phase will have eastbound left, okay, because they are conflicting, right? So they cannot be in the same phase. So one conflicting pair is this one, and the other conflicting pair is this one, okay. So this one gives you 630 and this one gives you 378, okay. So which one is more critical in the eastbound westbound case? The most critical one is 630, okay. Similarly, for the north and southbound case, okay, you have this pair, conflicting pair, which gives you 360, and you have this one which gives you 418, okay. So again, which one is more critical? This one is more critical, okay. So the total volume on the intersection, which you can pass, okay, in 4 different phases, is the total of these two, 630 plus 418. Okay, now keep in mind when these two phases are happening, because this concept will come later on as well, so let me explain it. When westbound through right happens, eastbound through right can also happen, because they are not conflicting, they can happen together, right? You can go straight towards east and you can go straight towards west, there's no conflict. So this and this can happen together, they are not conflicting, they are simultaneous. Same thing here as well. Left turning west and left turning east can happen together, so they can happen simultaneously, okay. So if I'm saying I will only pick 630 and not 378, 378 is automatically happening simultaneously. So when 630 are moving from one side, 370 are moving from the other side, so I don't need to worry about it, okay. So that's why we are just picking the critical one, because the other one is happening simultaneously, okay, it is happening at the same time, okay. So the total is 1048, okay. Now we did they give us the capacity? Capacity is not given, okay, so we'll pick one of these values. For example, you can pick 1400, more conservative value, okay. So now we can calculate V by C ratio. So V by C ratio will be 1048 upon 1400, okay. This is for one lane, keep in mind, this is for one lane only. So how much is this? Uh, 0.74, okay. So if you go to the table, okay, so we are under capacity, okay, and the delay will be very low, delay will be towards the lower side, okay. So this is the situation here, okay. Then we have this particular example, okay, it's very similar, okay, it's very similar to the one which we had earlier, okay. The only difference is in the lanes, okay, lanes in the north-south direction, okay. So when you are doing the north-south direction, okay, you will not do multiply by 0.5, because only one lane, okay. Here there were 2 lanes. If you go to this example, there were 2 lanes here. I was doing it multiplied by 0.5 to account for the 2 lanes. All directions had 2 lanes, okay. The left turning only had 1 lane, and these in all directions, right and straight, had 2 lanes, so I was multiplying by 0.5. Here for east west you will do the same, because east west has 2 lanes, okay. Where is it? Yeah, so east west has 2 lanes for straight and right, so you will do the same thing for east west, multiply by 0.5. But for north south you will not do it. North south is only 1 lane, so this whole thing 150 plus 60 will be taken as it is. So 150 plus 60 plus 80, okay. So it will be all in one, like they are already per lane, I will add them. This is hole in one lane and this hole is in one lane. So I don't divide by the number of lanes here. Okay. Got it or not? Any questions? So you will repeat the same process, but you will not do this multiply by 0.5 here. Okay. I had to do it because in this example for right and through all directions had two lanes. Okay, and I had to convert it to per lane. Or this is per lane. Okay, but in this example north south is just one lane for each case. Okay, so if I'm doing for example the pairs for the north south, it will be like this. One pair will be 80 plus 150 plus 60. Okay, and the other pair will be 170 plus 230 plus 120. Okay, this will be for the north south. Okay, and you will pick the maximum one from here. Okay, for the east west, you will still do the same thing. Okay, so you will take these two, okay, then you will add them together to get the total volume, and then you divide by 1400 or any other value, and then you will add the volume capacity ratio. Okay, is it clear or not? Any questions? Okay, now we move on to the real analysis of signal design. Okay, and in the end we are trying to find out the level of service for the signal, okay, which is called the operational analysis. Okay, finding out the level of service for any facility is called the operational analysis. So earlier we have done operational analysis for freeways, different segments, basic freeway, merging, diverging, weaving. And now we will do the analysis, operational analysis for signals. So these are 7 steps involved in it. Input data, then you look at the movements and the flow rate in each lane and so on and so forth. You have to find out saturation flow rate for each lane, find out the proportion of arriving vehicles during green time. Then you find out the signal phase duration if the signal is actuated. If it is not actuated, then you will design it yourself. Okay, it is fixed. Then you have to find out the volume, the capacity. You already have the flow rate. You will do the volume capacity ratio, and on the basis of that you can calculate delay and level of service. So we'll go through these steps. So what input data you need? Obviously you need the traffic data, and the traffic data you must have percentage of heavy vehicles in each direction. Okay, so traffic data should include percentage of heavy vehicles in each direction. And another thing which you need for each direction is peak hour factor. Okay, so for each direction you have to take traffic volume in a way that you can calculate later on percentage of heavy vehicles and peak hour factor for each direction. Percentage of heavy vehicles is very simple. You take the total and you count the heavy vehicles separately. You can calculate the percentage. For the peak hour factor, we have to do it in intervals of 15 minutes. So you don't take 1 hour full only. You have to divide this 1 hour into 15 minutes interval. So for each direction, you will have 4 values in an hour, one for each 15 minutes. So later on, these values can be used for calculating peak hour factor. Then you find out the geometry of the intersection, number of lanes, the lane width, the lane length, how many lanes for each direction, do you have any combined lanes, okay, and if the lanes are they separate or they are without any traffic island or something, okay. So these things, geometry of the intersection. Then the last thing is signal timing data, either you find it or you design it. The next thing is you should divide this into number of movement groups and lane groups, okay. So movement group is any number of lanes which have a common movement. Any number of lanes which have a common movement will be in one lane group, in one movement group, one movement group, okay. Lanes which have a common movement will be put in one movement group. First example, no problem, only one lane. Next example, I have two lanes. Do they have any common movement? The answer is no. So they are in separate movement groups. Third example, you can see again two lanes, but now they have a common movement in them. Both of them have the through movement. So now I put them in one movement group. Two lanes, same movement, one movement group. Three lanes, again a common movement in all three of them. So they will go in one movement group. Okay, so whenever there are lanes which have a common movement in them, they will be put in one group, and the lanes which have no common movement will be put in separate movement groups. Then we have the lane groups. Lane groups are those lanes which have similar capacity. So not on the basis of movement, but on the basis of capacity. Okay, so if you take the first example again, one lane, so I can only have one value of capacity. Next example, I have a left turning lane and I have a combined lane for straight and right. So they cannot be in one group. They have different movements, and that means they have different capacities as well. Whenever the movement changes, capacity will change. Whenever the movement will change, capacity will change, even if one movement changes. If you look at the third example, this one, now since they have common movement, for movement group, I can put them in one group. But lanes, they are in different lane groups, because this through is with left and this through is with right. Okay, so because the movement has changed, one movement has changed, one is common, but the other has changed. So the capacity will also change. So they are now in different groups. So the same lanes are in different movement groups. Same lanes are in same movement group because of the common movement. But because of the other movement which is not common, they are in different lane groups. Okay. This is in one group because both of them are left turnings. No difference in them. Again, one group because there is no difference in them. One group because there is no difference in them. Okay. So if all of them were on one intersection, then they will be in different lane groups and different movement. They will be in different lane groups. Okay. Now, can you tell me for this example, if these three, if they are in one intersection, I have two left turning lanes, two straight lanes, and one for straight and right. How many movement groups will I have? So they have already mentioned we have three lane groups. Okay, so in this intersection we will have three lane groups. Left turning will have its own capacity, straight will have its own capacity, and straight and right will have its own capacity. But how many movement groups can I have on the same intersection? Tell me. Two, yes. We will have two movement groups because these will be in one movement group because they have a common movement. Okay, so although their capacity is changing, but because of the common movement, they will be in one group. So we'll have 3 lane groups and 2 movement groups. Okay, so in summary, whenever you have a common movement, you put those lanes in the same movement group. Whenever you have any one movement which is different, you will put them in a different lane group. Okay, even if the other movements are common in them. Okay, so for the lane groups, I need all movements to be the same, not just one common movement. For the movement group, any one common movement is enough to put them in one group. Okay, so this is the difference, but lane group is more important for us. Okay, our signal design is on the basis of lane groups. Our signal design is on the basis of lane groups. Movement group is something which can help you in designing the signal or imagining the geometry of the intersection and so on and so forth. But the main thing for us is the lane groups, because we are playing with the capacity. So the next item in the list was how to find out the saturation flow rate for each lane group. We identified the lane group. Now for each lane group you should have a saturation flow rate. These two values which are given here, 1900 and 1700, are ideal values for per lane. Ideal values per lane. Okay, and they are the 1900 is for urban locations, the 1700 is for other locations. But these are ideal values and they should not be taken without due adjustments of the intersection. Okay, so you can say, okay, this lane has 1900 by default. Okay, but for the analysis, I will see if this value should be adjusted or not. Now you can see here the adjustments, all of them multiplied. Okay, and what are these adjustments? They are written here. So this is your ideal value and this will be your real value for the analysis. Okay, this one. Okay, so what are the adjustments we have? We have adjustment for lane width, adjustment for heavy vehicle and gradient, adjustment for a parking lane beside your lane, if there's a parking area beside your lane, like on the side of the road. Adjustment for local buses blocking the intersection. So if you have a local bus which is near the intersection, local bus stop, sorry, a bus stop which is near the intersection, the bus is supposed to stop at the designated point, and this is stoppage. So when the bus is stopping, it will go in and come out of the bus stop. So this can block the movement. So signal could be red, could be green, but people may have to wait for the bus to go in to the stop and come out of the stop. So this is the blocking effect of the bus. Then you have the factor for area type, factor for lane utilization. So if you have 2 lanes for the same movement, okay, if I go here, okay, so let's say two lanes for left turning, these two. So will they carry equal number of vehicles, both of them? It's not the case. Okay, so if you have like 100 vehicles total left turning, they will not divide by 50-50. Okay, drivers think differently. Okay, many of them may want to go with the extreme left lane. Okay, or if there's a U-turn, they may want to go for the next left turn lane, the middle left turn lane. Okay, but in any case, they will not be 50-50. So this is the lane utilization scenario, the lane utilization issue. Okay, that if multiple lanes share the same movement, how will the drivers divide in these lanes? This is called lane utilization. Then you have factor for left turning vehicles. If your lane is allowing for left turning, you have separate adjustment factor. Same thing for right turning as well, if your lane allows left turning. Then you have pedestrian adjustment factor for left turning group. As if you have left turning lane and the pedestrian crossing is allowed on the other side. Then factor for pedestrian bicycle adjustment for right turning lanes. So you can see now all adjustment factors will not apply to all lane groups. So for example, this one will only apply if your lane group has right turning movement. This one will only apply if your lane group has left turning movement. Okay, so some of them will not be applied. Then factor for work zone, we discussed work zone for freeways as well. So what is the work zone? Tell me what we mean by a work zone. What we mean by a work zone? Yes, anyone? Construction, yeah, construction site, construction on the road. Okay, good. So you know what is the work zone. Now then we have adjustment factor for downstream lane blockage. Okay, so what do we mean? We have two intersections. Okay, or let's say one intersection, whatever. Okay, and one of the lane is blocked here because of any reason. So this is called as downstream lane blockage. There's any blockage because of maintenance, because of anything. Okay, but it is downstream, after the intersection, not at the intersection. It is after. So after then, when you cross the intersection, now you cannot continue in this lane, you have to change your lane. This is called as downstream blockage. Okay, and then we have sustained spillback. This is the two intersection case. So you have one intersection. Okay, so spillback is the queue from this intersection is going up to the previous intersection. This is called as spillback. When the queue from one intersection blocks the upstream intersection as well. This is called the spillback case. Okay. Now the spillback, the downstream blockage, the work zone, we discussed earlier as well. The adjustment factors are applied to something to situations which are prolonging, okay, which go on for a long time. So if you have a lane blockage for 5 minutes, you will not apply adjustment factor for that. But we know that the lane, there is a check post or there is something which keeps blocking the lane for most of the day throughout the year, then we will apply the factor for that. Same thing with the spillback as well. You had an accident or the signal was not working, okay, and because of that on one particular day there was a spillback, but most of the year it is clear, so there is no spillback factor required. Same thing with the work zone. Okay, so the factors, rest of the factors are already for things which are continuous: bus stop, parking lane, pedestrian. Okay, so these are all things which are continuous, but for the other things you need to keep in mind that you only apply it if the thing is continuous. Okay, how do I get these factors? Okay, so these are tables which give you most of the factors, not all of them. So these factors, they require separate set of calculation. We are not going in those details right now. They require, if you go to highway capacity manual, you will find calculations for pedestrian bike factor, work zone factor, downstream lane blockage factor, spillback factor. So there's a lot of calculation involved here. So I'm skipping them. Okay, but if you are interested, if you are using a software, then it can do it for you easily. If you want to do it manually, you can go to the manual and you can go through the calculation. Okay, it's not difficult, and they have explained it with examples, solved examples. But we are skipping it in the course. Okay, the first factor was for lane width. It's very easy. 3 ranges are given. Based on these ranges, you pick up your factor. Okay. Second factor was for heavy vehicle and gradient. So if you are doing it for downhill condition, this is your equation. This is for level and uphill. So we have 2 equations. Okay. In both the equations, let me zoom in. We need percentage of heavy vehicles and need percentage of the gradient. Okay. Percentage of heavy vehicles, percentage of the gradient. Okay. Now see here, I'm subtracting them from 100 and I'm dividing it by 100. Now tell me, if my percentage of heavy vehicles is 4%, so in the equation I'll put 4 or 0.04. Tell me. And we will do the same thing with the gradient, what you will tell me for the percentage of heavy vehicles. In this equation, 4% heavy vehicles should go, PHV should go as 4 or as 0.04. What do you say? Okay. No, we'll put 4. See, we are already dividing by 100. Okay, you're already dividing by 100. So we'll put 4 here. Okay, you get my point. If I put 0.04 and then the equation itself is dividing by 100, you are dividing by 100 twice. Okay, so I put 4 here. And the gradient is 3%, I will put 3 here, not 0.03. Okay, so keep it in mind. Okay, the next equation, if you have a parking beside the road, okay, so you, directly beside the road near the intersection, okay, then you will use this equation to calculate the factor. NM is number of parking maneuvers and N is number of lanes in your lane group. Okay, now parking, obviously if parking is present, it will be on the right hand side of the road, right? So I will do it, I will apply this factor, parking factor, for the lane group which is on the right hand side of the road. If I'm doing it for a lane group which is in the middle of the road, on the left hand side of the road, then I don't need this factor. Okay, so going back to number of lanes, I'm doing it for the lane groups which are on the right hand side of the road, and I put the number for that, and NM is how many times vehicles come and go in 1 hour in the from the parking area, not on the intersection, the parking area. Okay, so NM is for vehicles which are going into parking and coming out of parking, which is beside the road in 1 hour. Okay, and obviously we are considering peak hour in all cases. Then we have the next factor for bus blockage. Okay, so we will use this equation. Okay, NB is the number of buses stopping per hour. Number of buses stopping per hour. Okay, for both these factors, they have given us a minimum value. Okay, so FP should be more than, FP should be, or cannot be less than 0.05. So this equation, if it gives you less than 0.05, you will take 0.05. Same thing for FBB as well. Okay, if the equation gives you a factor less than 0.05, you will take 0.05. Okay, so N is again number of lanes, and NB is how many times the buses are stopping per hour, and obviously it will be for the right hand side of the road. Bus stop is also on the right hand side. Okay, then we have, if you are doing it for a central business district area, then the factor will be 0.9. If you are not doing it for CBD area, don't take this factor. Okay, so this factor is only 0.9 or nothing. Okay, 0.9 or nothing. Then you have the lane utilization factor, which will come from this table. So what type of lane you are doing? Okay, how many lanes in the group? Okay, and then you can take the factor from here. They have given us a distribution as well. This is extra information. Okay, so if you have one lane, everybody will go from that lane, right? If you have two lanes, so what they are saying, 52.5% will go from one lane and the remaining 47.5% will go from the other lane. So as I was saying, the distribution is not equal. Okay, if you have 3 lanes, so the maximum which will go from a lane is 36.7. okay, and the remaining two lanes will share the remaining 60 point something percent, but it will be less than, in each lane we will have less than 36.7%. So this percentage is the maximum a lane can have from the shared lanes. Okay, if you have more than one lane, then the maximum a lane will have is these percentages. According to these percentages, you will have your factor from here. Okay, so this will only be applied if you have more than one lane for one direction. Okay, if you don't have it, then this factor is not required. Okay, so lane utilization factor, factor for right turning, okay, 1 upon ER, where ER is 1.18. Factor for left turning, 1 upon EL, where EL is 1.05. These are equivalency factors. ER and EL are equivalency factors. We had equivalency factors for freeways in the case of freeways for heavy vehicles. Okay, so equivalency factor means what? The effect of this vehicle compared to a normal vehicle, right? In the case of heavy vehicles, it was the effect of a heavy vehicle compared to a car. In this case, this is the effect of the turning vehicle compared to a straight vehicle. Okay, so right turning has an equivalency factor of 1.18. That means what? Having one right turning is equal to having 1.18 straight vehicles, through vehicles. Okay, so equivalency factor is the meaning of equivalency factor. And the remaining four factors I told you, we are skipping their calculations because they take a lot of steps and time. Okay, so we're only focusing on the available factors which you can get easily. You can see all these factors are either given or they can be calculated with a simple equation. Okay, we have this example here. Okay, any of you have any questions? Any questions here? Is everything clear? Okay, so moving on to the example, we have protected left turning. Okay, I told you last time left turning protected means that you will wait for the signal to turn green, and if it is permitted, then you will make the turning when the intersection is clear. Okay, but this one is protected in the normal case. Okay, left turning cannot be done without the signal. Lane width is given. For each lane is different. Okay, for left turning lanes, two lanes left turning, it is how much? It is 11 feet. For through and right is 13 feet. Okay, volumes are given: 3% heavy vehicles, 1% gradient. There's the parking, you can see the parking area here. There's a local bus stop which is near the intersection. Okay, it's a non-CBD location, there are no bicycles. Okay, so let us apply the factors. First of all, it's a non-CBD area. They did not mention if it is urban or rural. Okay, I will assume that they are doing it for urban, so I will take S naught as 1900. Okay, then I will go through the other factors. The first factor is for lane width. Okay, now I have so I have to do it for left turning and then for the through and right as well. Okay, so I'm doing it for left turning. Let's say for the to start it, I'll do it for the left turning. Okay, so left turning, lane width factor. Left turning has 11 feet lane width, so I'm here. Okay, factor is 1. The next one is for heavy vehicles and gradient. I have 3% heavy vehicles, 1% gradient. Okay, and 1% is given as positive, so that means I'm level or uphill. Positive is positive, right? Yeah, positive. So positive means level or uphill. Okay, so I'll use this equation. What are the calling it HVG. So this is 3% as I mentioned earlier, and this will be 1%. Okay, so how much is this? How much is this value? Okay, 0.973. Moving on to the next one, which is for parking. Do we have parking for left turning? We don't have parking for left turning. So this factor is 1. 1 means if you multiply it, then nothing will happen, right? So I'm doing it for the left turning, that's why. Buses and bus parking nearby, again, left turning, will not count it. Is it a CBD area? It's a non-CBD area. Okay, so factor for area type, 1. Lane utilization, I have 2 left turning lanes. 2 left turning lanes. So 2 left turning, 2 lanes. Okay, my factor is 0.971. Okay, the next one is for right turning. Do I have a right turning lane? No, I have a left turning lane only. Okay, so FR will be 1, FL will be 1 upon EL, where EL is 1.05. How much is this? Okay, 0.95. Okay, any other factor I can use? Okay, the rest of the factors we are not doing it. Okay, and we don't have swivel back, we don't have lane blockage, nothing is given. Okay, so we can keep ourselves to this. Okay, so my S will be 1900 multiplied by all these factors. 973, 1, I don't need to multiply with 1. Okay, it will remain the same. So I'm just multiplying with the factors which can have a effect. The rest are 1. Okay, so this will give me for the left turning. For the through and right, okay, so this is for left turning, for through and right. Let us go through the list. Okay, where is it? Okay, for through and right, my lane width is 13 feet. Okay, so this one factor is 1.04. Okay, I have the same percentage high vehicles and the same gradient, so this factor will not change. Parking, I have parking. Okay, and so parking is on the right hand side lane, and I am doing it for the right hand side lane. So I will apply the parking factor now. Okay, how many lanes I have? I have 1 lane. Number of maneuvers, Okay, so nm is 0. Now you see here, no vehicles coming in or out in the peak period. Okay, so nm will become 0, the factor will not become 0. And the logic is you still have the parking area. So when the drivers are coming, they don't know whether the vehicle will come out or not from here. Okay, so there is an anticipation. It will affect their flow, even if no vehicles are coming out. Okay, so even if nm is 0, the whole factor doesn't become 0. Okay, so I'll just do 0 here. That's it. But the factor will still be there. Okay, so how much is this factor? Okay, 0.9. Okay, next factor is for bus. Okay, bus blocking. I have it now for the right hand side lane. So buses blocking, how many buses? 15 buses per hour. Okay, so I'll be using this one. So one lane minus 14.4, 15 buses. Okay, how much is this? Okay, 0.94. Okay, factor for area type doesn't change. Lane utilization factor, I only have one lane. Okay, I only have one lane, so this is not required. Do I have a right turning movement? Yes, I have right turning movement, so this will be 1 point. This will be this much. So how much is this? And the left turning will become 1 because there is no left turning here. Okay, so how much is the factor for right turning? 0.847. Okay, so if I look at it now, I'm multiplying with 1.04, 1973, then 0.94, then 0.847. Okay, how much is this? Okay, so you have the saturation flow rate for the two different lane groups. Okay, any questions? Do you guys have any questions in this step? Okay, so I hope it's fine. Moving on, the other factors, I believe, I don't know. We took 1900 as well, yes. I believe there's some rounding off here. Okay, so 9, we were taking 973, they are taking 974. Okay, so yeah. So for left hand side lane, we had 2 lanes. So for one lane, if it is this much, then for 2 lanes, it will multiply by this. Okay, this for left turning and okay, very close. Okay, the next thing is calculating proportion of vehicles arriving during green time. It depends upon two things: G by C ratio. What is G by C ratio? G is your effective green time and C is the cycle time. So G is for every phase, for every movement, you have small g. Small g is effective green. What does it mean? The time available for the vehicles to move. Okay, so the entire phase is not utilized by the vehicles. If the entire phase is 30 seconds, vehicles do not utilize full 30 seconds. Okay, they utilize maybe 26, 27 seconds. Okay, the remaining is lost time. So from the phase, if you subtract the lost time, it gives you effective green. Okay, from the total time of the phase, which you are giving to the vehicles, from that if you subtract the lost time when the vehicles were not moving, you will get the effective green. Okay, and the cycle time is the total time of the signal. Okay, total time of the signal. When all movements are completed, when all phases complete, this is cycle time. Okay. So movement time of one vehicle, effective green, upon the total time of the signal, G by C ratio. What is RP? It is called the platoon ratio. Platoon ratio. What is the platoon? Group of vehicles which pass the intersection together. The signal will become green. The vehicles from that side, which has green, will pass together, right? So those vehicles will be called as platoon. Okay, platoon. So RP is the ratio for the platoon. From where do we get RP? We have this table. Okay, so we just need to focus on the first two columns. These two columns, they give us the value. The remaining is explanation of what it means. So when you meet these values, what will it mean? It means this one. Okay, so you can see different arrival types are given: 1, 2, 3, 4, 5, 6. Okay, and then we have the spacing between the intersections. So between your intersection and the next one, what is the spacing in terms of feet? Okay, so arrival type, arrival type, the explanation is given here. Arrival type means that arrival type 1 means that signals are very close to each other, but the vehicles are still coming randomly. This is arrival type 1. Okay, then arrival type 2 is signals are far from each other and the vehicles are still coming randomly. 3 means signals are very far from each other and we still have random arrival. Okay, so in the last 3 we have the same things: signal close, somewhat close, very close, but the arrival type is coordinated. So the first 3 are random arrivals and the last 3 are coordinated arrivals. Okay, so signal which are very close to each other and the arrivals are coordinated. Signals which are somewhat close to each other and the arrivals are coordinated. Signals are far from each other, the arrivals are still coordinated. Okay, so the first 3 conditions are for uncoordinated, the last 3 conditions are for coordinated. Okay, in the uncoordinated case, we don't have anything less than 1600. Okay, like we don't have this range, less than 800. For the coordinated case, we have the extra value of 800 here. Okay, but as I said, you need to focus on this these two things. Okay, so 1, 2, 3 means uncoordinated, 4, 5, 6 means coordinated, and then you see the distance, and based upon that you will take your platoon ratio. RP. You put RP from here, G and C will come from the signal timing, and then you can calculate the platoon arrival on green. Okay, meaning the group of vehicles which arrive during green. So when they arrive during green, they will move on, right? They will not stop. Then if you have actuated signals, if you have signal sensors there, you have to go in the field and collect its timing. Then you calculate volume to, okay, we are over time. So you stop here, okay, and I will continue next time, inshallah. Anybody